So I want to talk about diodes. I'll tell you a little bit how they work, but mostly I just want to get into how you actually do the math with them and how you apply them and what they do. There's actually a video on how they work in the lecture, so you can check that out. It's pretty good. So we'll just delve right into like actually just doing the math and figuring out what they're for and how to actually, put them into a circuit. First thing I want to do is kind of talk to you about the diode itself and what it does. I'll draw a diode on the board, and essentially a diode is this symbol with an arrow that indicates the direction of current. Diodes allow current to go one way but not the other. Now if we actually look at the type of current that's going through, it's conventional current. So I'll draw that just so we're fresh about this. And by the way, I have to put a resistor in this circuit, and we'll talk about why that is true a little bit later. So right now we know that the current goes from the positive to the negative, right? Not really. I mean, it actually goes from negative to positive, but that's all Benjamin Franklin's, thank you, his fault. But we won't talk about that. But essentially, the way that we do all of the symbologies for devices, specifically diodes and transistors and diodes and triacs and all of these other cool things that are actually made of this NP type material, whatever that is, the symbology is such that it's designed for conventional current. So as you can see, this arrow is pointing this way, so it allows current to go this way, but it blocks current going that way. It's like a check valve, if you know what a check valve is. A check valve is actually the same thing, but for fluids. So what we're going to do is we're going to talk about kind of how to do the math here. And what I'm actually going to do is I'll just use this same circuit and it's my guitar. We'll just use the same circuit and we'll do a little bit of math. I need you to use your imagination right now. Just chill out. Think about a door. Now, it's not just any door, it's a door with like a spring on it. So for you to actually stand there and open that door, if you want to hold that door open, you have to use energy. So you're standing there opening that door. I want you to envision a diode as just a door. It's either open or closed. Now let's get into voltage drop and what that's all about. And we know it's really connected to energy. So I'll just I'm going to throw a really basic series circuit up here. So I've got a resistor here and I've got a resistor there. And let's say that's 10 volts and this is 100 ohms and that's also 100 ohms. We know that the voltage drop across each one of those is going to be 5 volts. And we know that the voltage drop exists because of this. We know voltage is energy per coulomb. So the voltage drop is actually dependent on how many coulombs are going through it. The voltage drop is also actually dependent on that. If I were to increase that to 20, that would be 10 volts and that would be 10 volts. So there are some things that change the voltage across this. And actually we know the other thing is that we know that V equals IR. So the current going through that will also change the voltage drop. So the voltage drop across this changes actually depending on how much current is going through or how many coulombs are traveling through that. And really it's all boils down to the amount of energy that's required to push current through at a certain rate or a certain amount of coulombs through. So my point here is that the voltage drop across a resistor is dependent on the resistive nature of the resistor, the current going through the resistor, and the voltage supply. So with all that said, you understand that, and that's nothing new to you. I want to talk about the voltage drop across a diode and why that exists. Now, just a standard diode, the voltage drop is going to be 0.7 volts or it can be 0.3, but we'll just roll with 0.7 right now. These numbers actually can change, but let's roll with an example of 0.7 volts. That is dependent on the type of diode that it is. That's actually called the forward voltage bias. Let me label that. So the voltage on this diode forward equals 0.7 volts. I'll take that off. So that's the forward voltage. Now, by the way, that's the amount of voltage that it uses. Now, voltage is energy, right? Okay, so that's the amount of energy that it uses to actually stay open. So just imagine that door again. You're holding that door open and you're using a certain amount of energy. Now, let me ask you a question. Depending on how many people are going through the door, we can say that's like the flow rate going through the door. Okay, so if like one person went through the door per minute, you'd still be standing there holding the door open, using a certain amount of energy all the time to hold it. And if like 20 people went through the door in a minute, you'd still be standing there using the same amount of energy. So this thing, this door, this one-way door, or it's either kind of opened or closed. If the people are trying to get out, you close the door. Okay, that's a whole other thing. But what's going on here is that to hold this open, this needs at least 0.7 volts to open up or to allow current to go through. Once it has that, it's always using it to allow current going through. And whether there's actually no current going through or a lot of current going through, it doesn't change the nature of the amount of voltage required to allow it to continue the current, to let the current travel through. So the voltage drop across this is not dependent on this. Let's make that 10 volts. And it's also, let's actually put some value here. Let's call this 1000 ohms. We're going to call that R1. So we actually now have some voltages here, some values here. And I could change that, and I could change that. And this voltage drop across here would remain 0.7. I guess the only thing is this. If I were to change this down to 0.5 volts, then essentially what's going on is that this guy is not going to have, it's not going to open up. It's not going to allow any current to go through it. Actually, the voltage drop across that will still be 0.5. So no matter what voltage you put on here, you'll see it. And as soon as you get to 0.7, it will stay at 0.7. And if I kick that up to 10 or even 0.8, that'll still be 0.7. And the reason, this is actually important that we look at this, why this is going to say 0.5 when I kick that down to 0.5. Let me, 0.5. 0.5 volts. If that's 0.5 volts, then this guy is closed. No current is traveling through. And we have no voltage drop across this at all because there's no current going through it. And you know that voltage is the energy pushing the coulombs through. If there are no coulombs pushing through here, then there is no voltage drop. So if that's 0.5, that thing doesn't allow current, there's no current going through there, there's no voltage drop across that. So with that concept, let's actually kind of look at how Kirchhoff's laws work in this situation. And you'll see this working in a moment here. I'm going to crank this up to 10. No, I'm going to crank it up to 1 volt. So now, if this is 1 volt, then this actually has 0.7 volts. It is now open and allowing current. When I say open, it's kind of like a door being open, or a switch being closed allows current to go through it. So just deal with my terminology. This thing is open, it's allowing current to go through it because it has more than 0.7 volts. So now current's going through it. Now let's take a look at something. Current's going through this. What's the voltage drop across that? And how do I calculate it? Well, I just used Kirchhoff's laws. Kirchhoff said that Vs equals VR1 plus VR2 plus VR3, but we can actually write it a little bit differently, and we can say Vf of the diode. So the forward voltage across the diode plus the voltage drop across this equals this. So essentially the voltage drop across this is going to be 0.3 volts. The voltage drop across that 0.3 volts because that's 0.7 and my source is 1. Let's kick these numbers up to some values that we can kind of use and see working, a little bit more tangible than 1 volt. Let's see if we can apply Kirchhoff's laws and Ohm's law and do some math with this. I'm going to leave this at 10 volts. Okay, good. So now we know, because of Kirchhoff's laws, the voltage drop across this is going to be 9.3 volts. Okay, so that's fine. So I'm going to say VR1 equals 9.3 volts. Nice. Can I use Ohm's law? Well, absolutely. I mean, we've seen Ohm's law work everywhere, in series and parallel, and we developed power formulas with Ohm's law. Ohm's law pretty much works, like, period. So let's put Ohm's law here. Okay, so I want to know the current going through this guy. Actually, I actually want to know the current going through this. Can I use Ohm's law to solve the current through this? Well, the answer to that is no. Because Ohm's law requires resistance. And the reason that we have a voltage drop across this is because of its resistive nature. And the function of the resistive nature of this is actually to take the electrical energy and turn it into heat energy. So we can use Ohm's law because that's going on, but we can't use Ohm's law here. And the way that the function of this thing actually is to take this electrical energy and turn it into actually light energy and or some heat energy as well. But it's very small, but it doesn't do that because of resistance. It actually does that because of the way it kind of manipulates the electrons. And you'll see that in that other video when you take a look at the theory behind these. But my point here is we can't use Ohm's law here because one thing is the current doesn't change depending on the nature of the diode. It just doesn't matter. As long as it's open, the current just goes through. The thing that defines how much current is going through is not the diode, but it's actually the resistor in the circuit. Now, we can't use Ohm's law here, but I know that it's a series circuit, and if I want to know the current going through this, I can just calculate the current going through that. Okay, good. So, if I wanted the current going through this, I'm just going to do this. I'm going to say IR, or I could say I equals I, the diode, the forward bias current through the diode. I could say that, or I could say even IT if I wanted to. But that's going to be this. It's going to be VR divided by R. So in that case, it's 9.3 volts divided by 1,000 ohms. And I'll put that down here. That's 9.3 milliamps. So there's actually 9.3 milliamps going through that diode. That's how you calculate the current through a diode. That's how it works, and that's how we actually do the math with this stuff. So with all that said and done, there's really nothing more that we could do here. Now there's a couple more things. We can actually calculate the power here. And the way we do the power is actually we just know the current and the voltage. And we know that power is current times voltage. So if I wanted to actually know the energy being dissipated over time, then I would just take the current, there you go, and I'd multiply it by that, and that's my power. Other than that, there's nothing really else we could do here. It's that simple. But there's one more thing we can do is we can change the nature of this diode and use another diode called a LED. Okay, let's talk about LEDs.